Hey everyone, you're not going to want to miss this episode of the AI Show where we are going to be talking to Beju from the ONNX Runtime team, and he's going to show us how we can start doing on-device training with the ONNX Runtime engine. Let's jump in. We are joined by Beju. Thank you so much for being here. Why don't you tell us a little bit about who you are and what you do at Microsoft?
Hey, Cassie, it's great to be on this show with you. Thanks for having me. I'm Beju. I'm part of the ONNX Runtime team, specifically working on training. Most people think of ONNX Runtime as an inference accelerator and know about its cross-platform compatibilities. But very few know that ONNX Runtime also supports training workloads and accelerates training scenarios for a large variety of models. So I'm part of the ONNX Runtime training group, and I'm here to talk about on-device training.
That's cool. So I'm excited to get to talk to maybe about some of the less known and newer features within ONNX Runtime. So there's accelerating for training, with like large transformer models. But now we're going to be looking at more of the smaller models that you can run on device. And there's a lot of benefits to doing on-device training. But if you don't know what it is, why don't you, can you tell me a little bit about what on-device training is?
Yeah, sure. So on-device training refers to having the ability to train deep learning models on devices, on edge devices, such as mobile phones, gaming consoles, or even web browsers. And over the past few months, our training group at Microsoft ONNX Runtime team has been working hard to add this capability to train deep learning models on edge devices. And that's what on-device training is all about.
That's cool. And the benefits of the cost savings for running on device, the data privacy because the data never leaves the device. The updated model also stays on the device, right? There is ways I think to kind of push that stuff off the device when you need to, but the latency, right? It's better for latency for on device as well because you're not making any calls out. And then the limitations are all obviously the hardware size and how to optimize for that.
Yeah. So for this show, I've prepared a demo that walks us through how we can start from a forward-only ONNX model and go all the way to deploying the models on the Android application and doing the local training there. So in this demo, we'll be using the transfer learning capabilities. We'll be starting with the MobileNet V2 model in PyTorch, exporting it to ONNX, creating the training artifacts. And this Jupyter notebook leverages all of these steps that I just mentioned. And we'll walk through them one at a time. So to begin with, we pull the MobileNet V2 model from PyTorch and export it to ONNX, keeping in mind that we're moving from 1,000 classes at the output to just 4, because in our scenario, we're going to do image classification with 4 classes, with 4 labels. And so, as you can see, the first step is exporting the model to PyTorch, to ONNX from PyTorch. And this should create an ONNX model in the training artifacts directory. Okay, there we go. So this created the MobileNet V2 model. Okay, so here's the forward-only ONNX model. As you can imagine, this is the MobileNet V2 model. So it has a bunch of convolution layers. And the final classifier layer, which is gem, has 4 labels associated with them. And for the purpose of this demo, we're just going to be training the last layer, the classifier layer. So the rest of the model weights remain intact. Only the last layer model parameters will be learned or trained, so to speak.
So we're able to just grab this pre-trained model, open source, from the Torch Vision API. And then now we have that, and that's our base model that you've exported. And now we're just going to be able to update that last layer with our local device on training. That's kind of the high level of what you just did.
Yeah, that's right. We're just going to we will be training the last layer and keeping all the remaining model parameters intact.
All right, cool.
So now that we have the forward-only ONNX model, it's time to create the training artifacts. And so for that, we have the ONNX runtime.training.artifacts utility that helps us do this. The first thing is we're going to load the forward-only ONNX model that was stored in the training artifacts repository, define the parameters that requires gradient computation. That's going to be the last layer's weight and bias. And all the other parameters are going to be frozen or constant, so to speak. They will not be updated while the training happens on the device. With those parameters, those variables set, we can call artifacts to generate artifacts, provide the ONNX model, provide the requires gradient parameter, frozen params. And for the purpose of this model, we're going to use the softmax cross entropy loss function. We're going to use the AdamW optimizer, and we're going to save all these artifacts to the same training artifacts repository. And when we run this cell, that should generate all the necessary models or the artifacts in the training artifacts repository. So we'll walk through each of them one at a time. So first, let's look at the eval model. The eval model is basically the same as the forward-only ONNX model, except for the fact that the last layer has a loss attached to it, which is the softmax cross entropy loss. But the remainder of the model remains exactly the same. Next, let's look at the training model. So the training model is very similar to the loss model, with the distinction that after the loss, we have the gradient graph for the classifier weight and classifier bias. So this is the gradient graph attached to the eval model, and that defines the training model. The optimizer model is a very simple one. It takes in the parameters and the gradients and updates the gradients in the direction of updates the parameters in the direction of the gradients. And this is the learning process in the on-device training. And finally, we have the checkpoint folder, which encompasses all the model parameters, trainable as well as non-trainable, so that they are not embedded within the ONNX model. So they are shared across the training model and the eval model. These will be the 4 training artifacts that we will need to deploy to the device to, in our case, the Android application for on-device training.
So those are kind of the high-level steps that you need to do. Now, when it comes to choosing the loss function and the optimizer, that type of stuff, those are things people can kind of play around with to see what they need for their scenarios, right? But there kind of tends to be, like, these are probably the more widely used ones for this type of task, right?
So these are customizable. Users can attach a loss function of their liking. We offer a few out of the box, but if the user wants to, if the developer wants to define their own custom loss function, they can do so and just provide that as an argument to this function.
Okay, so these artifacts are part of the ONNX Runtime library that you're setting here?
Yes, exactly. All of this is part of the Runtime training library.
Cool. So now we're ready to actually see how we take this and do the training in the application itself, right?
Yeah. So now with these artifacts generated, we are ready to perform training. Before we go into the Android application, let's just see if we can actually train using these artifacts and prove that this kind of transfer learning is possible on the mobile NetV2 model. And so we will do this experimentation in Python. As I mentioned before, ONNX Runtime training offers Python bindings in addition to other language bindings, so that we can test out our solution on our local machine before we actually go into writing the application. And so we have this a Jupyter notebook called train, which takes these assets that we developed and that we generated in the previous step and learns to classify animals, in our case, learns to classify between dog, cat, elephant, and cow. And so the process is really simple. We do some pre-processing, again, some more pre-processing, define the number of epochs and the samples for each class. As you can see, we only need 20 examples for each class, and we run it for 5 epochs. And here is where we interface with ONNX Runtime's training API. So we import ONNX Runtime.train.api. And there are 3 important classes that the training API exposes. The first is the checkpoint state. The next is the module, and the last is the optimizer. The checkpoint state can load the checkpoint artifact that was generated earlier and loads all the model parameters defined within the checkpoint artifact. The module class takes in the training model, the checkpoint state that we just created, and the eval model, and will be responsible for orchestrating the training. So functions like train step, resetting the gradients will be exposed through the module class. And finally, the optimizer takes in the optimizer model and is responsible for exposing functions such as optimizer step, which essentially means updating the model parameters in the direction of the gradient. As you can see, the optimizer takes in the optimizer model as well as the module that we just created here. After setting up these three variables, these three objects, we can define our training loop. And over here, we iterate over 5 epochs, and within each epoch, we run through 20 examples per class and run the model. So we compute the training loss by providing the input images and the labels to the model. We take the gradient step or the optimizer step, and then reset the gradients for the next computation. And we can run this. And at the end of each epoch, I'm outputting the loss, the training loss.
So now this is the logic that we need to take those assets that we created and actually run that training loop. And now we're doing it in a Python notebook, but this is going to be the same steps you would follow for implementation in any of the supported languages, right?
That's right. This is a proof of concept showing that training is possible with our artifacts. It's a way to expedite experimentation. So instead of doing all the experimentation on the device application, we do it offline to prove that such training is possible. And then once we have our experimentation done, we can just port over what we've done in Python to the application. So in this example, the Android application. And as you can see, after each epoch, we have the loss going, the training loss decreasing.
Mm-hmm. And this could also be used then for them to figure out what the right amount of epochs and sample images and that type of thing for their scenario, trying maybe different loss functions, things like that. So this is like our development loop for building our model and how our model is going to learn on our device.
That's right. All the hyperparameters, loss function, the learning rate, and anything that is specific to the training scenario, training solution for our users, can be experimented with in this offline phase before actually going to the application development phase.
Great.
Cool. So now that we have a trained model, the next step is how do we know whether this model works in the real world? And for that, we expose a functionality which is exporting the training artifacts for inferencing. So given a trained model, we can export that trained model to an inference-ready ONNX model. And then after doing that, we just load up this inference ONNX model with the existing ONNX Runtime inference session and perform inferencing with that. And okay, so here, after setting up the inference session, I can run a quick test to make sure that our model works well. So as you can see, the input image that I provided is one of a dog, and our model predicted with 61% accuracy that it is a dog. So it seems like we can actually use the MobileNet V2 model, the pre-trained model, only update the last layer so that we relearn the parameters in the last layer to use it for an application of our choosing, to classify images of labels of our choosing.
Okay, so we saw how you were able to do on-device training with your customized images and get this response. How does that compare to the accuracy of the model without any additional training? Like, how is it performing before we did this additional step?
Okay, so yeah, that's a good question. So we can just basically load the original ONNX model and test out whether the original ONNX model performs well or not. So here I've just copied over the same block as earlier, with the one difference is that instead of loading the training model exported to inference model in the inference session, I'm going to load the original ONNX model. So you can see over here, I'm loading the training artifacts MobileNet V2 model. So this is the original forward-only ONNX model.
Okay.
And then, so let's run this. And then if we call predict on the same test image, we can see that it gives random accuracies for each of the 4 classes. Mm-hmm. And in this case, it actually predicts that the given image is that of an elephant.
So yeah, we got a lot better results. I mean, it's kind of an elephant, not really. Maybe if it had a little bit longer trunk, I think, but it's definitely a dog. Okay, cool. So that really showcased nicely the power of just a little bit of extra training on some customized or on some images, custom image sets to improve the performance of the with on-device training.
Yeah, so I think at this point, we've showcased that we can actually use the MobileNet V2 model, fine-tune it for our needs, and learn to classify images of any classes that we really want to do, that we want to really classify. Now we can extend this application and learn to even classify images of ourselves, for example. So we could learn to distinguish Cassie from Beju, for example. And I think the Android application will strive to do that. So let's just try to see how we can do that in the Android application. Yeah, so here I've opened up Android Studio and loaded the code that's available in the ONNX Runtime Training Examples repository. Also note how I've copied over the assets that we created previously in the offline Python script and added them to our assets folder in the Android application. Just head over to the two important functions in this application. The first one being training. So so here I defined the training loop again. And it's pretty much the same as the one that we defined in the Python script. The number of epochs are 5 and batch size is 4. So we process 4 images at a time. And so yeah, we loop over the number of epochs and our input data. We do some pre-processing, and then we call perform training. And this is where we interface with ONNX Runtime. So we go into this ORT trainer class and look at perform training. The first thing to note is the constructor. We create the ORT environment using ORT environment or get environment. We create the training session using the environment that we just created. So ORT env.create training session, provide the necessary checkpoint paths, training model paths, evaluation model paths, and optimizer model paths. And now we're ready to perform training. So this perform training function creates the input ONNX values, so the input tensors for training that are that can be comprehended by ONNX Runtime. And we call ORT training session.train step and provide the inputs to that. The inputs are going to be the image data and the labels associated with those image data images. And we can get the training loss as output from this train step call. So after getting the training loss, we can call training session.optimize the step and training session.lazy reset grad, which will reset the gradients. So as you can see, this is pretty much similar to the way we defined the training loop in Python. And the other function of interest is the perform inference one. So here, what we do is once we've completed training the model, if we create the inference ready ONNX model from the trained model. So we call ORT training session.export model for inferencing, provide the model path where we want to save the inference model to, and we are ready. And this will generate the inference ready ONNX model. And that's pretty much it. That's how we interface with ONNX Runtime.
That's cool. And I think that anyone's probably worked, if you've worked with like image classification, this all looks really super familiar. And if you've worked with ONNX Runtime inference sessions, even that having the training session, but it's still following a lot of the same like things that you would expect, the steps that you would expect to happen.
Yeah.
Now I said you went straight from like you created your inference model and then you created your session. Is that model saved? Like, is it output to the device too? Or
Yes.
are you just doing that all in memory?
So currently this will output it to a file location on the device.
Okay.
We are preparing a solution where instead of only outputting to a file, we can also get it in memory. So that's not available yet, but we are working on that.
What are the kind of device requirements for running training? Will it run on anything as long as there's enough memory to do it? Is there, or I guess, how are the constraints around local training considered within the training API?
Pretty much on-device training will work for any device that our ONNX Runtime inference solution works on. The only limitation is that you don't want to train at a time when the user is probably interacting with the device. So you don't want to slow their functionality or impact the device functionality in any way. So you would probably train during idle times when the device is plugged into a charger or at night when there isn't much activity on the device. But the ONNX Runtime training on-device training solution should just work for any Android application or any Android device that our ONNX Runtime inference session works for. Inference library works for, yeah.
Cool, that's awesome. All right, I think I have a good idea of how we now can take the logic and implement it into a Java application. Would be really similar with the other APIs that are supported, like C#, soon to be JavaScript as well with the ORT web. But I would love to see this work on the Android, and I think you have a demo of this working, right?
Yeah, so let's just jump into the demo. So for this demo, we are going to learn to classify images of 4 popular celebrities: Tom Cruise, Brad Pitt, Ryan Reynolds, and Leonardo DiCaprio. So as I mentioned earlier, we can use the same transfer learning technique and learn to classify images of custom classes And over here, I'm doing that with celebrities. Now you can see that I'm actually I'm trying to predict the celebrities, but it got it wrong on the test images that I provided it. That's because we've not yet started the training process. Um, and now we're feeding in images for each class. We're feeding in 4 images, 16 images per class for Tom, Brad, Ryan, and Leo. And we start the training process. In the training process, we are looping over these 16 images per class for 5 epochs. And at the same time, doing all the pre-processing and post-processing and all of that. And now we are ready to perform the inference. You can see that after exporting to inference, we can actually learn to predict the celebrities correctly.
So for people that were watching and really want to get started and try this out, where can they go to learn more?
So I think ONNX Runtime.ai has a really good getting started page. It links to our blog, which goes into depths into our architecture. So it has a link to this current blog that I'm over. It kind of explains the trade-offs, the benefits of on-device training, and when to use it. It also has some instructions on how to get started with the different language bindings, how to install the libraries, um, and also has a link to the tutorial demo that we presented today. So I think that would be a good place to start.
Awesome. So we got everything you need on that link that we're showing below. You can go there, read the blog to get a more detailed look at what we were showing you. There's those examples on the GitHub. Lots of ways to get started with this. And again, Beju, thank you so much for joining today and showing us these really neat features for how to train on device in ONNX Runtime.
Thank you, Cassie.